So our last video for the week is on higher order partial derivatives. So if you remember back when you had a function of a single variable, you had a first derivative and then you had a second derivative. So you can kind of ask, how does the second partial derivatives work? Well, right, you're taking the derivative, the partial derivative of f with respect to x, and then you can take the partial derivative again of that with respect to x. So the way we can denote this, there's two other options. You can write partial squared f, partial x squared, or you can write fxx. You could do the same thing but for y, so take the partial derivative of f with respect to y, and then whatever you get back, you can take the partial derivative again with respect to y. fyy. But you have another option. You don't have to, when you have two variables, so you don't have to, when you take your second partial derivative, you don't have to use the same variable. So for example, you can do the partial derivative of f with respect to x, and then take the partial derivative with respect to y, partial squared f, partial y, partial x. This is fxy because you took the partial with respect to x first and then with respect to y. Or you could have done the opposite. You could have started by taking the partial derivative with respect to y and then take the partial derivative with respect to x, partial y, and this is fyx. And these last two, where you're not taking the same variable when you're using your partial derivatives, these are called mixed partial derivatives. So let's look at an example here. Find the second partial derivatives of the function f of xy, which is 3xy squared minus 2y plus 5x squared y squared, and determine the value of fxy negative 1, 2. So you're going to find your partial derivative with respect to x first. fx, it'll be 3y squared plus 10xy squared, and find fy, 6xy minus 2 plus 10x squared y. So these again are your first partial derivatives, but now we're going to find our second partial derivatives using those. So take fx and then take the partial derivative with respect to x now. So you'll get 10y squared. Take fx and take the partial derivative with respect to y. So it'll be 6y plus 20xy. Take your partial derivative with respect to y, and then take another partial derivative with respect to y. You'll get 6x plus 10x squared. And then take your partial derivative with respect to y, and then take the partial with respect to x. It'll be 6y plus 20xy. And then I was asked to find f of xy negative 1, 2. So we're going to plug it in. You'll get 12 plus a negative 40, so negative 28. Now you might notice something that happened here. I don't know, I didn't go into detail or mention it, but if you look right here, these were exactly the same. And you might wonder, is that always true? Well, we started with a special function. We had a polynomial function in our last example. And what's so great about polynomial functions is that they're continuous. And so that's actually what happens if your function f is a function of x and y such that fxy and fyx are continuous on an open disk R, then for every x, y, and r, f of xy equals f of yx. So these functions in our last example, these ones here, they were polynomials which are continuous everywhere. And so that's exactly why they were equal. So let's look at our last example. I want us to show that f of xz equals f of zx and f of xzz equals f of zxz equals f of zzx for the function f of xyz equals y e to the x plus x ln z. So if I look at my partial derivatives here, I only need x and z. None of these contain y. And so I'm going to start by finding fx. So I'm going to write my function y e to the x plus x ln z. Find fx, y e to the x plus ln z, and then find fz, which will be x over z. And now I need, looking back, I need xz and zx. So fxz, so maybe I'll just write fxz here. Now take the derivative here with respect to z, you'll get 1 over z. And if I take fz, take the derivative with respect to x now, fzx, you'll get 1 over z. And notice that these two things are, in fact, equal. That was one of the things we needed to show. I'm also going to need fzz for the next step. So I'd get negative 1 over z squared. X. The coefficient there is x, negative x over z squared. Okay, and then from here, looking back at what we need to do, we've already done this part here, but we still need to do this part. So I'm going to take this one and find fxzz, take the derivative with respect to z, negative 1 over z squared. Here, take the derivative with respect to z, negative 1 over z squared. And then here, if I take the derivative with respect to x now, it would be negative 1 over z squared. And again, these three things here, 1, 2, 3. These are all equal.